In this video, we're going to be looking at red-black tree deletion. And most of the presentations of red-black tree deletion I see involve double black and some things like that, which I think is a bit non-intuitive. So this is a different approach. Some of the transformations are different, but they do keep the red-black tree legal. And so I am going to present this, and you can see if it makes sense to you. Okay, let's review red-black tree definition. A red-black tree is a binary search tree, which means that every node in the tree has a left and a right subnode. It could be null or empty. And also, all the elements in the left subtree are greater than the root of the subtree we're looking at, and all the elements that are to the right are greater, and that applies recursively. In a red-black tree, in addition, every node is colored either red or black. And the root, if we have an empty tree, of course we have no nodes. But if we do have even one node, it'll have a root node, and that root node has got to be black. That's part of the red-black tree definition. And we have two other rules involving, one involving reds, one involving blacks. No red node may have a red child. So we cannot have two red nodes connected to one another. So that's this rule here. And finally, that if I look at any null subtree at the bottom of the tree, any null at the bottom of the tree, and I chase from that null all the way up to the root and count the number of black nodes along any path in the given tree, that number has to be the same. We call that being black balanced. So for example, we have this tree. This is a valid red-black tree. This has a black height of 3. No matter where we start, okay, we have a number of nulls here. These little gray circles at the bottom are nulls. If I start at this gray circle and start counting black nodes up to the root, 1, 2, 3. If I start at this gray circle right here and start counting black nodes up to the root, 1, 2, 3. If I start at this gray circle, this null down here, count black nodes, 1, 2, 3. So this is a red-black tree whose black height is 3. We also notice that the root is black, and that I don't have any situation where we have two red nodes connected to one another. It's also a binary search tree. Here I have a 35. All the nodes that are less than 35 are on the left side. All the nodes on the right side are greater than 35, and that applies to any subtree. So this 75, all the nodes below it to the left are less than 75. All the nodes below it to the right are greater than 75. And so if I want to find a particular value in the tree, I can start at the root, I can compare, and if the value I'm looking for, let's say, is 60, I can start at the 35. Well, the 60 is greater than 35, so I go to the right. The 60 is greater than 55, I go to the right again. 60 is less than 75, I go to the left. 60 is less than 65, and there I find my 60. Okay, so that's basically a review of the definition of what a red-black tree is. Now, I presume that you have already looked at insertions, but I'm going to review the insertion fix-up rules. When we have red-black tree insertion, we insert a red node in a leaf position, but that may cause a red-red violation because the place it belongs may be connected to another red, in which case we have to do a fix-up. The reason I'm reviewing these is not because we're going to go back and do insertions, but the scheme I'm going to present, sometimes when you do a transformation, it ends up putting two reds together, and then we have one last step that's going to be to apply one of these rules to fix up the red-red so we don't have a red-red. So the goal is to start with a tree with a certain black height, and in this example, all of these triangles are presumed to be subtrees that all have the same black height, and they are black rooted or they may be null. So they might be all null, in which case they have black height of 0, or they might be black-rooted nodes and they all have the same black height. Okay, so in this case, it would be a black, it would be following the black height rule, because if all of these subtrees have the same black height, all of them have one additional black here, which means this is black balanced. And so this has a consistent black height on both the left and the right. Okay, when we have a red-red problem, what we do is we'll consider, this is the red that's presumably been inserted, and so we have a red child, we have the red parent, and that's where the red-red problem is. And what we do is look at the grandparent, and then on the other side of the grandparent is the uncle. And if the uncle is red, what we do is we simply flip the colors in the top three. Okay, and this should be reviewed to you if you've looked at red-black tree insertions. And so we end up with a tree like this. Now the problem here with insertion is it's possible that this guy might have had a red parent, and that would cause a red-red problem up here. But it turns out when we're using these transformations in the context of deletion, we're going to never end up having a propagation like that. And so, but we will end up in a situation where we may see a red-red in this context. And what we do is we simply do a recoloring of these top three nodes, and so it looks like this. The other two cases is if we do not have a red uncle. In that case, we have either a null uncle, or a node that's black, a black uncle. In which case, we look and see, is the position of the two red-reds, does it kind of make a line? And so going from the grandparent to the parent and then to the child, is it all going the same direction? In this case, it is. And by the way, all of these have mirror image transformations if the red-red is on the opposite side. In this case, we do rotation. And again, all of these are either null or black-rooted subtrees of the same height. And we simply rotate the B over A. And rotation should be something you're very familiar with if you've studied red-black tree insertions. And so we end up with this. We also, there's a recoloring that goes on. Basically, the node that ends up being the root is colored black. And the node that was the root, that no longer is, A in this case, gets colored red. And so we end up going from here to here. And this gives us a tree of the same black height. Okay, the black height of this tree is the same as the black height of this tree. But it now has eliminated the red-red. And similarly, if I have this last case here, the direction from the grandparent to the parent is different than going from the parent to the child. We call it a jig. In that case, we do a double rotation. Basically, B rotates over C, and then B rotates over A. So B gets pulled up between the A and the C and becomes the new root. And we get something that looks like that. And in this case, again, the node that becomes the root is black. The node that was the root and no longer is becomes red. And so there's recoloring evolving there. And so we're going to be using, actually, we're not going to be using this one. We'll be using case A here and case C. Those will come up. Sometimes we'll need to do a red-red fix-up, basically, to eliminate a red-red as part of the transformation. Okay. So now let's get on to deletion. When I want to do deletion, the first thing we need to do is basically do a deletion, or just a regular binary search tree deletion. And when we do that, we have basically three cases. We have a case where the node we're deleting has two children, a fully interior node. We have a case where a node has one child, and we have a case where we have no children. If we have no children, we can simply delete the node in the case of just a regular binary search tree. In the case where we have one child, we can simply remove our node and replace it with its child in the position of the tree. When we have two children, we need to do an in-order successor or in-order predecessor copy. I'm going to use in-order successor just so I have something algorithmic, and we always do the same thing. Basically, I take the in-order successor and I replace the data from the in-order successor replace the element, and then delete the in-order successor in its leaf position or its near leaf position. So let's look at some examples of this. So I have a node with two children. So 35 has two children. And so if I want to delete the 35, I will look for the in-order successor. The way we find that is I go right once and then left as far as possible. And that gives us the node that is the next numerically higher node in the tree from the 35. And what we do is we take this value 40, we copy it into the 35 position. That removes the 35, and now we have two 40s. And then we delete the 40 that's down kind of in this leaf or near leaf position. Okay. Now, if this is a red-black tree, this causes a problem because it's not isn't black balanced anymore. But we'll deal with that later. We're just talking right now about the how to find the in-order successor and what to do with that. Okay. So that's two children. If I have a node with one child, I simply do a replacement. So in this example, let's say I want to delete the 15. Okay, well, I'd find the 15 by finding it on the way down here. I want to delete the 15. What I do is I basically replace it with its child. So in this case, the 20, instead, since I'm deleting the 15 here, the 20, instead of having its left child be the 15, it's going to have its left child be the 10, and the 15 goes away. Okay, again, in this example causes a red-red problem, and so, but right now we're just looking at what we would do in a regular binary search tree, not in a red-black tree. Okay, and of course, if we have a leaf node has no children, then I can simply, if it was a regular binary search tree, I could just simply delete it. For example, the 50 here has no children, so I could just delete it, and I would be done. Okay, let's undo some of those things. In the case of red-black tree, we have to be a little more careful. Now, in the case where I have two children, basically, we do the in-order successor copy, and that basically is going to transform the problem into case 2 or 3 or 4 below, because the in-order successor is always going to have at most one child by definition. Since we go to the left until we can go no farther, it's never going to have a left subtree. So it's either going to have one child or no children. So in the case of a red-black tree, the two children case, we do the in-order successor thing, and that converts it into 2, 3, or 4. Okay, so that one's pretty easy to do. If we have a node with one child, in this case, we're presuming we already have a legal red-black tree. And so I can't have a red node with just one child because it's not going to be black balance, or it'll have a red-red violation, one or the other. And so the situation here is it must be a black node of the red child, for example, in this case. So what we do here, if I have a black node with a red child, I want to delete the black node. What I do is I simply replace the black node with its child, but then I color this guy black. Okay, so this guy goes away. And that restores it to a legal red-black tree. From the shape of the tree point of view, I've just deleted a red node. And so I'm still black balanced, I don't have a red-red problem, etc. If I have no children, then it depends on whether it's a red node or a black node. If I'm deleting a red node, I can simply delete it and I'm done. So let's say the 30. I want to delete the 30 from this tree. I will compare the 30 to the 40 to the 5 to the 20. I will eventually find it. I will see it has no children, and I can just go ahead and delete it, and I am done. Okay, so cases 1, 2, and 3 are pretty straightforward. It is case 4 that is the challenging one, because what happens? So we delete the child, we delete the black node. So let's say we're trying to delete the 70. Okay, compare the 70, compare the 70, compare the 70. I eventually find it. I go ahead and delete it, but now I am out of balance, because if I start at this null and count my black nodes up to the root, I have 1, 2, whereas I start at any other one, like this one or any one, I will count 1, 2, 3. So any of the other paths will have 3. So I have a problem here, and I need to basically do a fix-up. So the fix-up transformations are basically for the situation where I have a tree where I'm out of balance, okay? Either I've just done a deletion and this side's black height of this subtree, which is null, so 0, is different than this subtree's black height. It will differ by 1, and I will need to do some kind of a fix-up. And that's the situation that I will be in. And that's where I need to do a fix-up. And so that's where the focus of this is going to be. This is what we've seen so far has kind of all been preliminary stuff. Okay, so the case where we're deleting a black node at a leaf position causes an imbalance problem. And that's the situation we're going to try to deal with. Before we look at the transformations, I'm going to do a little bit of terminology that we're going to be using. So the situation we are in is that we will have a node that's a subtree, and this could be null. And this is the node, basically. This is going to be the short subtree, and this is going to be the larger subtree. So this is in terms of black height, that this one will have black height 1 less than this, and therefore we have an imbalance. And the goal is going to be to increase the, basically, have the same tree, but have the black height be the same in both, and ideally have this tree, this side, increase so it's the same as that. And now we have our tree, and everything is good, because originally, I have the root of the subtree here, and these guys originally had the same height, which is the height of this. We've made a modification to this that has shortened it, for example, by deleting a black node, if it's a single black node. And now we want to do a fix-up so that we again have these guys restored so they're the same height they're both the same height as they originally were. And most of the time that's going to work. But the notation here is the node in question, that's the root of the short tree, which indeed could be null. And it's going to have a parent, so this is going to be our parent. And then we also have our sibling. This is the sibling. And then we have what I'm going to be calling the nephew. The nephew is the child of the sibling that's farthest away from the node in question. And the niece is the child of the sibling that's closer to us. So if the shortness is on the left, we'd have parent, sibling, niece, nephew. Here is the flip side. Here the shortness is on the right, is the mirror image. And here we would have parent, sibling, nephew, niece. Okay, so these are the 4 important nodes. And so what we're going to do is we're going to have a shortness coming up here, and we're going to determine what transformation to do. And the algorithm is going to be, I start looking for a red node from the top, and I go down and look at all of these. So if my parent is red, I will do transformation number 1. And we'll talk about what the transformations are just in a bit. Otherwise, if the sibling is red, I do transformation number 2. Otherwise, if the nephew is red, I will do transformation number 3. Otherwise, if the niece is red, I do transformation number 4. Otherwise, if all of these guys are black or null, and the nephew and niece could, one or both of them could be null, then I will do transformation number 5. And so that takes care of all the cases. When I've seen transformations involving, double black and things like that, there have been a number of transformations, and the way to determine what transformation to do looks at a combination of some of these nodes. Here, it's very simple. You look at the parent, then the sibling, then the nephew, then the niece, looking for the first red you see, then you know what transformation to do. And it turns out the first 2 transformations might introduce a red-red violation, in which case, after the transformation is over, if there's a red-red violation, you then apply a red-red fix-up after that. But in transformations number 1, 2, 3, and 4, you do the transformation, you're done. There's not going to, from case 1 to case 4, and that transforms into case 6. There are not these multiple transformations that you do at the same level. The exception is transformations 1 and 2. Sometimes you end up having to do a red-red fix-up, but then it's only one red-red fix-up. It's not like in insertion where a red-red fix-up might cause a red-red violation higher in the tree. In this context, you do one red-red fix-up, and that's it. You don't have to you don't cascade them. You don't have to cascade. And the transformation number 5 is one where it actually it balances this tree, but the way it balances the tree is not by making this guy larger to match this like the original. It actually shrinks this guy, so they're both the same, but now this whole tree has shortened in black height by 1, and so we need to do a fix-up at the next level up. And so transformation number 5 is the only one that causes us to go to a higher level. Okay, so what are the transformations? So our fix-up transformations to fix up the shortness, and I'm only doing these for the shortness on the left. If the shortness on the right, we basically just do the mirror image. Okay, the shortness on the from the left, if the parent is red, and in this scenario, if I have a black triangle, it indicates a subtree that is either null or is black-rooted. And if I have an open triangle with a red star in it, that means it could be any red-black tree. It could be red-rooted, it could be black-rooted, it could be null. Okay, so that's the situation here. And also, all of these have the same black height. In a given diagram, all of these have the same black height. So in this case, we can see that there's a shortness here because these 3 guys all have the same black height, but these 2 have a black node above it, and this guy doesn't have a corresponding black node. Therefore, by definition, this subtree has a shortness. Okay, so this is number 1. This is the red parent case. The red parent case, all we do is we rotate the sibling over the parent. Colors stay the same. And that fixes this up. The one possible problem we could have is if this subtree is red-rooted, that means that I now have a red-red violation, and so I follow it up by doing a red-red fix-up. Let's see, let's actually go to an example of this. Here is an example. These 2 examples I just have up here for, if I want to delete a red node, that takes care of things. If I want to delete a black node that has a red child, I can simply delete that, turn that guy black. But here's the case that is in question. So here's the shortness. Okay, this subtree has a black height of 1. This subtree has a black height of 2, and I have a red parent. Okay, red parent. I rotate the black child over the red parent. Okay, and what that looks like in practice is this guy comes comes down here and connects in this way. And this is now my new subtree. And it's now everybody has black height of 2. So that's our first transformation. Second transformation. Here, I look at the parent, it's black, so I look at the sibling, it is red. In this case, we have a double rotation, and we also have a recoloring. Similar to what we'd seen in the red-red limitation transformations, what happens is that the node that becomes the root turns black. So here C is going to become the root, it turns black. The node that was the root becomes red. So here, basically I have a double rotation. What happens is C rotates over A, and then B rotates over A. And the result ends up looking like this, where A ends up dropping down 2 levels, it becomes red. And that's the transformation. Again, there's one situation. If this subtree is red-rooted, I'm going to have a red-red problem here, and then I do a red-red fix-up to solve that problem. This one, I sometimes, because the A drops down 2 levels, and the A and the C switch colors, I sometimes call this a color swap and double drop. I do a color swap here, and then the A drops down 2 levels. So it does a double drop. And so here's an example of that in action. Here is the short tree. Here's the larger tree in terms of black height. Here the shortness is coming up here. I look at the parent is black, but the sibling is red. So I color swap these guys, and then I drop this guy down 2 levels, and that will come down to there, and they connect in this way. I'll straighten them out in a little bit here. And so this is what my new tree looks like. And in this case, both sides here have a black height of 2, and with the black root, the entire tree has a black height of 3. Third case. Here, again, I have the short tree here, because this guy does not have the extra black above it, whereas these 3 all do have the extra black above it. So if I counted black starting from here, since these guys all have the same black height, that I would be 1 short if I come up from here compared to coming up through any of those. So in this case, I look at the parent, it's black. I look at the sibling, it's black. But I look at the nephew, and the nephew is red. And in this case, what we do is we color the nephew black from red and just do a single rotation. And that takes care of the problem. And so we go from there to there. Here is an example of transformation number 3. This is the short side. This side has a black height of 1. This subtree has a black height of 2. Together, we want it to have a black height of 3. We basically want this side to also have a 2. So when we put it together with this, the whole thing is a black height of 3, which is what it was originally before we did the deletion over here. That's caused this guy to have the shortness. So I look at the parent, it's black. I look at the sibling, it's black. I look at the nephew, it is red. So I color the nephew black. And then I rotate the sibling over the parent. And that gives me that. And now everything is nice and balanced. I have a subtree here of height 3. the fourth case. In the fourth case, here's where we have the red niece. So here, the niece is sitting here. It's kind of jigging in. In this case, there's a double rotation. Okay, the B rotates over the C, then the B rotates over the A. So the effect is I split up the A and the C. I pull the B out, and it comes up above everyone else, and then everything, I just set the links so they fall into place in order. And what we end up with is this right here. And the niece turns black. Nobody turns red here. So as an example of that, we will look at this subtree. So here's the shortness. Coming up here, parent is black, sibling is black, nephew is black, but niece is red. So we color the niece black, and basically we disconnect the niece from everything. Also disconnect the parent from the sibling. The niece comes up, and then everything here falls into place, and we have a subtree that looks like this. This is basically effecting a double rotation. And that is the result there. Last transformation. Here, nothing is red. Not the niece, not the nephew, not the parent, not the sibling. And so here, all four of those are black. In this case, what we do is we basically, these guys are black-rooted or null. So we do a recoloring. Basically, here we give up and say, there's not a red here that I can use to make this tree the black height I want. So I'm going to balance this, but I'm going to balance it by making the entire tree one less than I want, which means I'll have to, there'll be an imbalance problem up at the next level, and I will have to go through this same set of transformations and apply the appropriate one at the next level. So in this case, here is the shortness. I look at parent, black, sibling black, nephew black, niece black. I color the sibling red. Now this is all balanced, but the problem is it's balanced, but the whole thing is a black height of 2, not a black height of 3, which means that if this is connected to some higher tree, then the opposite side of this is going to be imbalanced. So we need to apply the same transformation at the next level. So that's basically what is going on here. Okay, so if you want to take a break, that would be a good time to do it, because what I'm going to do now is I'm going to go through and take a tree and basically start out with a tree with, 20 nodes or so, and I'm going to successively delete nodes from the left and watch the tree continue to be a red-black tree at every step and see it go into nothing. I'm going to take the same tree and I'm going to delete nodes from the right. So the first case, lowest to highest, the next case, highest to lowest, and then I'm going to start in the middle and do the same thing. Anyway, so we will take a look at that. Here's our tree. It is a black height of 3. If I look at any null here, I count the blacks up to the root. 1, 2, 3. 1, 2, 3. 1, 2, 3. It's a binary search tree. This is one we actually looked at before. But at this point, we are going to start deleting nodes. So I'm going to start deleting nodes from the lowest number to the highest. And that means we're going to start deleting the 0. Okay, so delete the 0. We have a shortness coming up now on this side. We need to fix it. What transformation do we do? Well, the parent is black, but the sibling is red. That corresponds to transformation number 2, where the red sibling And this is the one I call color swap and double drop. So I swap these colors, and this becomes the new root. And this guy drops down 2 levels, and we splice that in here. And this becomes our new red-black tree, except this introduced a red-red problem. So in this case, we need to fix that. In this case, this is the child, this is the parent, that's the grandparent. The uncle over here is null, it is not red. And this is one that does a jig. And so this ends up being case 3 in red-red fix-up. This is actually the mirror image of the one in the picture here. Basically, the B becomes black, the A becomes the new node that's going to become the root becomes black. The node that was the root becomes red. I pull this guy above the other two, and that ends up, so this guy becomes black, this guy becomes red, this becomes the root of that little subtree, and these two guys become the children, and that now restores this to being a red-black tree. Okay, well now we delete the 5. Well, it's red, so we would officially delete it by searching from the 35, finding the 5 down here, and by comparing and getting down here, but it's a red leaf, so we just delete it, and we're done. Now we want to delete the 10. Delete the 10, this is the situation where we have a single child, and so we simply replace the parent with the child. We're deleting the 10. I simply do what I call a single leaf replacement. This guy becomes black and replaces the parent, and here we're done. Next one, 15. 15, we delete it. We now look, parent is black, sibling is black, but nephew is red. Red nephew, that corresponds to transformation number 3. We color the nephew black and do a single rotation. So color the nephew black, we do a single rotation, which basically means that this guy comes down here, and that takes care of that. We again have a valid red-black tree. This looks really imbalanced because this guy's got the minimum number of nodes, and this guy's got a lot of reds that lets it spread out, but it's a valid red-black tree. Next one to delete is going to be the 20. So we delete the 20. Okay, now we look at the parent, it's black, the sibling is black, and both children are null. There are no red nodes anywhere around. That corresponds to transformation number 5. So that means let's look at this again. The sibling gets recolored to be red. But in transformation number 5, it's basically shortened the entire tree. This is a balanced subtree, but it's one shorter than it's used to be. It used to have black height 2, now it has black height 1, which means now we have a shortness here that we have to deal with. Shortness coming up here. We look at the parent. It is black. The sibling is red. Okay, in this case, it's transformation number 2. It's our color swap and double drop. So we change the colors of those two, swap the colors of those two. This guy drops down 2 levels and gets spliced in right here. And now we again have a valid red-black tree whose black height is 3. Next one, we delete the 25. Well, this has got a single child, so we just do the standard single child replacement. We basically replace the 25 in this case with the 30, and we color the 30 black, and we are done. No transformations necessary. Now we decide we want to replace the 30. We want to delete the 30. Delete the 30, well, that was black, so that causes a shortness to come up on this side. The parent is red. Parent is red, that is transformation number 1. We simply rotate the sibling over the parent. So that basically means we rotate sibling 40 over the parent, which is 35. And that gives us, again, a valid red-black tree. Now let's delete the 35. Well, it is a red leaf, so we can just delete it, and we're done. Next transformation, we delete the 40. We delete the 40. That leaves a shortness coming up from this direction. We look at the parent, black, sibling black, niece and nephew are both null, so they're not red. So that is transformation number 5. And so that means we color this guy red, but that means there's a shortness that's coming up to the next level. And so now we look at the parent here at this level is black, the sibling is black, but the nephew is red. That's transformation number 3. And for transformation number 3, we simply color the nephew black and do a single rotation of the sibling over the parent. Color the nephew black, and we do a single rotation of the nephew over, the sibling over the parent. And that gives us something that looks like that. And again, we have restored this to being a red-black tree. Next transformation, our next deletion. We have 45 to delete. Well, it's only got a single child, so we do our standard single child replacement of replacing the parent with the child and coloring the child black. And again, we have a valid red-black tree. Here we have 50 we're going to delete. Well, here we have a shortness coming up here. Parent is black, but sibling is red. That is transformation number 2, which we basically take the root, drop it down a couple levels, do the color swap. So color swap and double drop. So these two guys swap colors. This becomes the new root. And this guy drops down 2 levels and is sitting right there. And there we go, another valid red-black tree. I'm going to stop looking at these at every one, figuring that we've had enough practice now. So let's go ahead and delete the 55. Well, 55 is easy. It's a red leaf, no problem at all. And now we're going to delete the 60. Delete the 60, shortness coming up here. Black, black, no reds anywhere. This guy turns red. That's transformation number 5. But that means that we have a shortness that propagates to the next level. And so we look at parent, black, sibling, black, nephew, niece, all black. So in this case, we apply transformation 5 at this level. And so this guy turns red. And at this point, we're at the top. And so there isn't anything to be imbalanced about. What this has basically done is it's turned the red-black tree into a red-black tree of height 3, into a black height 3, into one of black height 2. Okay, next task is to delete the 65. Well, the 65 has got a single leaf. We do the standard single leaf replacement. And that gives us a valid red-black tree. We now delete the 70. That was a black node that we deleted, so there's a shortness coming up here. The parent is black, but the sibling is red. That gives us our color swap and double drop. And now again, we have a valid red-black tree. We now delete the 75. Takes care of that. It's red, so nothing else to do. We now want to delete the 80. Well, that's got a single child, so we do our single child replacement, which we color that guy black and replace. And now we have another valid red-black tree. We now have the 85 we want to delete. That was a black leaf, and so we want to, we have a shortness coming up here. Black, black, no reds anywhere, so this guy turns red. Transformation number 5. We have another valid red-black tree. And now I want to delete the 90. In this case, it is a I've got a single child, so I do the single child replacement. Turn this guy black, and this guy gets deleted, and this guy replaces it. I now have just the 95 in my tree, and when I delete the 95, it turns it into an empty tree. So that takes care of the deleting things from lowest numbers to highest. Now let's try same tree, and let's delete the numbers from highest to lowest. So we'll be going from right to left this time. So we'll start out deleting the 95. We'll do the same thing. We'll basically take it down to an empty tree. So 95 is deleted. It is black. And so I have a shortness coming up from this side. When I have such a shortness, what I do is I look at the color of the parent. The parent is red. That means I do transformation number 1. That is a sibling over parent rotation. So that gives me this. But in this case, it causes a red-red problem. And so I need to do the red-red fix-up. Well, this is the case where we do not have a red uncle here. And so basically, and it's an inner jig here. So what I do is basically the 85 is going to become my root. And so I color it black. What was the root becomes red. I pull the 85 up, and the other two fall underneath it. And I now have another valid red-black tree. Delete 90, that's a red leaf, that's easy. Delete 85, that's a single child, so I can just do the single child replacement. That is easy. I now delete the 80. That causes shortness because it was a black leaf. Parent is black, but sibling is red. What that means, I do my color swap. And double drop, and that brings it down here. And again, I have a valid red-black tree. I now delete the 75. Red leaf, no problem. Delete the 70. That causes a shortness from this side. I look at the parent black, sibling black. The children are null, so they're not red. And so that's transformation number 5. Color this guy red, but that means at the next level, I need to do another fix-up because I have a shortness coming up here. Parent is red, in which case all I need to do is transformation number 1, which is rotate the sibling over the parent, which I will do. Rotating the sibling over the parent gives me that. I again have a valid red-black tree. Delete the 65. Well, it's got a single child, so I do my single child replacement, coloring the child black, and it replaces its parent. I delete the 60. Deleting the 60. I have a red parent. That's transformation number 1, which means we rotate the sibling over the parent and end up getting that. Delete the 55. It's a red leaf, no problem. Now I want to delete the 50. It was a black leaf, so I have a shortness coming up here. There are no reds anywhere in sight here. That's transformation number 5. So this becomes red. I need to propagate the shortness up to the next level. Here, that's the parent. It's black. Sibling is black. Nephew is black. The niece is red. In the case of a red niece, we color it black. We do a double rotation, which can be affected by disconnecting it from everything, also disconnecting the parent and the child. The niece becomes the new root of the subtree, which in this case is the entire tree. And the subtrees fall and get connected, falling into place like this. And this is my new red-black tree. I want to delete the 45. It's got a single child, so I do a single child replacement. Now I want to delete the 40. So I delete the 40. Shortness coming up here. Black parent, black sibling, null, which kind of counts as black nephew, but I have a red niece. So in this case, the niece turns black, and it becomes the root of that subtree, and everyone else falls into place like that. Okay, have red-black tree properties are restored. Delete the 35. I have a shortness coming up here. I have no reds anywhere here, so that guy, we do transformation number 5. This guy turns red. That causes the shortness to propagate up here. Black, 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 black. All 4 of the nodes we care about are black, so this guy turns red. And this is the place where the entire tree has its black height reduced from 3 to 2. Next, we have the 30 wanted to delete. It's got a single child, so we do our standard single child replacement. Here, we have the 25 to delete. It was a black leaf, so we have a shortness coming up here. Black parent, but red sibling. That's transformation number 2, which is our color swap and double drop. So color swap and double drop. And this is our new red-black tree. I want to delete the 20. 20 is a red leaf. That's very easy. And now I want to delete the 15. 15 has got a single child, so I do the single child replacement. I want now next to delete the 10. Delete the 10. It was a black leaf. Shortness coming up here. No reds anywhere. Transformation number 5 says make the sibling red. I don't need to propagate the shortness up anymore because I'm already at the root. In this case, the entire red-black tree has had its black height reduced to 1. Next thing I do is I want to delete the 5. It's got a single child, so I do the single child replacement. And now I have just the 0 here. If I delete that, it makes the tree empty. In this case, what I'm going to do is I'm going to start with the 30, and I'm going to leave the 0 through 25 alone at first. I'm going to start deleting in order, increasing from 30 to 35, etc., etc., just increasing by 30, 35, 40, 45, etc. In increasing order starting at 30. And then once we finish that up, we will work on deleting these guys. Okay, so we start by deleting the 30. What's a red leaf? That one is very easy. Now I want to delete the 35. The 35 has got 2 children, and so I need to find the in-order successor. I do that by starting the 35, going right once and left as long as possible. That gets me to the 40. And so I copy the 40's data in over the 35. Now the 35 is gone, which is good, but I have 2 40's, and I delete the 40 down here, kind of in this leaf area. And it happens to be black, which causes a problem because I have a shortness coming up here now. Well, I fix that by looking at parent black, sibling black, neither niece or nephew are red, so that's transformation number 5. I make this guy red, but that causes the shortness to propagate up here. In this case, the parent is red at this level, so it's transformation number 1, which says to rotate the sibling over the parent. And so I will rotate the sibling over the parent. This guy ends up dropping down to there. And now I see there's a red-red problem here, so I need to fix that up. Here, I have the child, the parent, the grandparent, and the uncle. The uncle is red, therefore I simply do a color flip of these 3. That corresponds to the transformation up here. Case A, where the uncle is red, I simply swap the colors of the three things at the top, no rotation necessary. And now I, again, have a valid red-black tree. Okay, next thing I want to delete is the 40. For the 40, it's got two children, so I find its in-order successor, go to the right once, to the left as far as I can, that's the 45. I replace the 45 there. The 40 is gone, but now I have two 45s. I delete the one down here. It has a single child, so I do the single child replacement, making that guy black. And there is the new red-black tree. I now delete the 45. Find its in-order successor. So to the right once, to the left as much as possible. I get to the 50. 50's data gets copied into the 45. And now I delete this 50. It was black, so it causes a shortness here. I look at the parent, it is black. I look at the sibling, it is red. That's transformation number 2, our color swap and double drop. So that comes there, and this guy drops down 1, 2, and that is our new red-black tree. For the next one, I want to delete the 50. Well, 50 is got two children, so I go to the right once, left as far as possible, finds the 55. 55 gets copied up into that location. And in this case, I now need to delete the 55 that's down here. It's a red leaf, so it's very easy. I simply delete it. I now want to delete the 55 from this tree. It's got two children. Find the inner successor by going to the right and then left as long as possible. The 60 copies into here. I now need to delete the 60 that's down here. That was black, and so I have a shortness coming up here. Parent is black, sibling is black, no reds anywhere. This guy turns red, but transformation number 5, which we just did, causes shortness to propagate up one more level. So I need to do another transformation. I start by looking at this level now. If the parent is red, well, that's all I need. I will do a rotation of the sibling over the parent. So the sibling becomes the new root of the tree, and the parent becomes the left child over here, and I end up in that situation. Red-black tree properties are now restored. I now want to delete the 60. So I go to the right and then left as far as possible. That's the 65. I copy the 65's data up here and now delete the 65. It has a single child, so I do a single child replacement. And again, have a valid red-black tree. Let's delete the 65. 65. Find the inner successor. Right, left, left, left. And finally find the 70. Do the data replacement here. Delete the 70. Shortness coming up here since it was black. Parent is red, therefore I rotate the sibling over the parent. And that gives me that. Again, I have a valid red-black tree of height 3. Next one, 70. Delete the 70. It has two children. Find the inner successor. It's 75. Copy the data. Delete the 75 down here. It's red. No other changes necessary. I now want to delete the 75. Find the in-order successor. It is 80. And so I copy the 80 over the 75. Delete this 80. Single child. Do our standard single child replacement. And I now have a red-black tree property is restored. Next, I'm going to delete the 80. It's got two children, so I will find the inner successor, which is the 85. Copy the 85 there, delete the 85 down here. It was a black leaf, causes a shortness coming up here. Parent is black, sibling is black, no red found anywhere here. So I do transformation number 5, which colors the sibling red. But that means I need to apply transformation up here at the next level. Shortness coming up from this side. Parent is black, sibling is black, nephew is black, but the niece is red. So when I have transformation number 4 here that I do, coming to there, transformation number 4. This is we're doing the mirror image of it, but basically the niece turns black. I do a double rotation. So color the niece black, and the way that double rotation is affected is that basically this guy comes up between those two, and those two become his children. So we will disconnect our niece from everyone, and also disconnect the parent and the child from one another, or the parent and the sibling from one another. Oops, didn't get that disconnection quite made. There we go. And I connect these two guys now, and these two subtrees fall into place like that. And this is the new red-black tree. Red-black tree of height 3. I now want to delete the 85. I found the in-order successor. I go to the right and then to the left as far as possible, which is nowhere. So the in-order successor actually is the 90. So the 90 gets copied there. Delete the 90. It's got a single child. So I do the single child replacement. Color the child black. It replaces its parent. And here I am with another valid red-black tree. I now want to delete the 90. The 90 is sitting here, but it's got 2 children. The in-order successor, go to the right and the left as much as possible. Well, I just go to the right. There's no left to go. So this is the in-order successor. So copy the data. This guy gets deleted. In this case, I have the shortness coming up here. No reds anywhere in sight. That's transformation number 5. This guy turns red. Shortness now propagates up to here. Black, 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 black. All 4 of these guys are black. Transformation number 5 again. So the node 5 turns red. In this case, I'm done with the transformation. If this had been part of a subtree, I would have to go and do the transformation on the next level, but I'm at the root, and so I don't have to worry about balancing anything else. The effect of this is the entire red-black tree's black height now is 2, not 3. Okay, delete the 95. To delete the 95, I see it there. It's got a single child, so I do the single child replacement. Delete the 95, and now I have finally gotten my red-black tree with all the numbers greater than 30 have been deleted. Okay, well now let's start deleting. Let's start deleting from right to left here. I'll start deleting the 25. Okay, so we'll delete the 25 now. He was black. Shortness comes up here. Black parent, but red sibling. That means we do a color swap and double drop. There's the color swap, and we drop this guy down by 2, and this is now my new red-black tree. Delete the 20, that's easy because it's a red leaf. Delete the 15, well, it's got a single child, so I do the single child replacement. Delete the 10, black leaf, shortness coming up here, no reds anywhere, transformation number 5, this guy turns red. And at this point, I have a 5 as a root. I want to delete the 5. And, well, I've got a single child, so I do a single child replacement, which basically means the 5 goes away, and the 0, the child replaces it. And now I just have a single node. If I want to delete that, that empties out the tree. And so that's more example of how this red-black tree deletion works. I hope you found this helpful, and you know, practice with these things. I think it's kind of fun to play around with these things, and hopefully this gives you a good understanding of one way to implement red-black tree deletion.